Welcome to my professional development presentation for mathematics. My concept is location and direction, spatial thinking in measurement and geometry. Where in the world would you rather be? Canada? Europe? The Middle East? Let's keep it local for this exercise. Picture the sun setting over the ocean. It's December, wet season, and the nights are hot. You are sweaty and the air is muggy. How would you describe your location? Are you on the east coast or the west coast? Are you up north or down south? How do you know? If you were picturing Broome or somewhere similar, you just used a number of spatial reasoning skills, spatial thinking, and spatial awareness concepts to picture yourself in this abstract location. Spatial thinking is integral to everyday life. People, natural objects, human-made objects, and human-made structures exist somewhere in space, and the interactions of people and things must be understood in terms of locations, distances, directions, shapes, and patterns. Here is an example of a question from a spatial reasoning test. In order to figure out the answer, you have to visualize 2- and 3-dimensional images in your mind and mentally manipulate these images into the shape you want. In regards to mapping, spatial reasoning tests are designed to assess your ability to take instructions to follow a map. These questions usually take the form of 2-dimensional map or plan, which you'll be asked to navigate. Spatial reasoning is the ability to think about objects in both 2 and 3 dimensions and visualize the movement of objects or deduce patterns between them. Spatial reasoning skills are a critical part of science, art, and math, and can be improved with practice. Spatial thinking or reasoning involves the location and movement of objects and ourselves, either mentally or physically in space. It is not a single ability or process, but actually refers to a considerable number of concepts, tools, and processes. According to the National Research Council 2006, spatial reasoning involves 3 components: concepts of space, tools of representation, and processes of reasoning. It involves understanding relationships between spatial structures and, through a wide variety of possible representations, from drawings to computer models, involves the means to communicate about them. Spatial thinking plays a fundamental role through the K-12 curriculum. Whether it's the learning of science, maths, art, physical education, or literacy, spatial thinking skills are important. For example, high school chemistry requires students to understand the spatial structure of molecules. Physical activity calls on students' awareness of the body position in space with respect to other objects, such as a dodgeball. Art, of all forms, is filled with opportunities to engage our spatial skills, whether it is playfully manipulating shapes and forms while painting, or representing musical notes spatially. Of particular importance, however, is the role of spatial thinking in mathematics education. Research findings across education, psychology, and neuroscience reveal a close link between spatial thinking and mathematics learning and achievement. In the Australian curriculum, students become numerate as they develop the knowledge and skills to use mathematics confidently across other learning areas at school and in their lives more broadly. Numeracy encompasses the knowledge, skills, behaviours, and dispositions that students need to use mathematics in a wide range of situations. It involves students recognising and understanding the role of mathematics in the world and having the dispositions and capacities to use mathematical knowledge and skills purposefully. The key ideas for numeracy are organised into 6 interrelated elements in the learning continuum, including spatial reasoning. The numeracy capability identifies spatial reasoning as an element involving students making sense of the space around them. Students visualize, identify, and sort shapes and objects, describing their features in the environment. They use symmetry, shapes, and angles to solve problems in authentic context and interpret maps and diagrams, using scales, legends, and directional language to identify and describe routes and locations. In developing and acting with numeracy, students visualize 2D shapes and 3D objects and interpret maps and diagrams. The structure of the Australian curriculum mathematics, measurement and geometry strand describe the concept that students develop an increasingly sophisticated understanding of size, shape, relative position, and movement of two-dimensional figures in the plane and three-dimensional objects in space. Developing spatial thinking, reasoning, and awareness concepts are important for students in Year 4 and 5, as they must use directions to interpret information and describe routes using landmarks and directional language. Teachers can use the resource I developed in Part 1 to overcome challenges and misconceptions related to the spatial concepts location, distance, and direction. The resource is designed to explicitly teach cardinal directions and how they can be used to describe location of a relative object or ourselves in space. So who needs to think spatially? Besides the fact that we all need to navigate our way around a three-dimensional physical world, careers in sciences, technology, engineering, and mathematics require strong spatial skills. Spatial thinking is also strongly employed in many of the arts. Architecture, graphic design, computer sciences, biology, physics, chemistry, geology, geography, and even medicine when you consider the spatial reasoning required to understand various ways of mapping the body, such as X-rays and MRIs, all require strong spatial skills. Spatial thinking involves visualizing, interpreting, and reasoning using location, distance, direction, relationships, movement, and change in space, thus presenting numerous common misconceptions or challenges that present barriers to learning for some students. Young children may begin to understand relative distance and spatial relationships, such as near, far, on, in, inside, around, between, and beside, yet struggle knowing which way to hold a map, and get easily confused if it is not aligned to the real world. More complex spatial concepts, such as metric distances and cardinal directions, begin to emerge in early primary, but students may not be proficient until upper primary. Barriers for these students may include transitioning from topological concepts of distance to metric measurements and scale, or being able to use landmarks and relative direction, but struggle transitioning to cardinal directions. Upper primary students are developing the ability to reason logically and make concrete connections to their world, however, may need guidance developing spatial understanding of all the resources available to determine locations, such as map scales, metric distances, and cardinal directions. Key features of teaching strategies that promote the ways of working in mathematics and have a positive impact on student learning include providing quality instructional resources and activities for learning how to think spatially. Concepts scaffolded through concrete, pictorial or representational, and abstract representations. Effective instructional resources should first focus on hands-on activities and concrete materials, such as the use of blocks, toys, puzzle maps that introduce basic spatial thinking and encourage the use of spatial language. Children should work with maps of familiar places, such as the home or schoolyard, that are large in size and scale. Symbols should be realistic interpretations that children can easily interpret. Learning is enhanced when there is social interaction or real-world action involved in spatial activities. Children should create and analyze their own self-made maps of familiar places before they engage in tasks where they are using maps developed by others. Young children should be provided with materials that promote sensory experiences and tactile, hands-on, active mapping activities, materials that provide simple maps large in size to allow children to explore with their whole bodies, and materials that provide opportunities to practice with maps of familiar places. Lower primary students should be provided with materials that provide bird's eye views of maps, and materials that provide pictorial and panoramic views of maps, materials that provide hands-on activities that allow children to manipulate maps, materials that produce more complex spatial concepts with explicit support, and materials that encourage students to produce their own maps and use maps and models that allow active exploration. Upper primary students are developing the ability to reason logically and make concrete connections to their world. Resources for students in years 5 and 6 should review basic spatial language, but focus mainly on advancing students' knowledge of spatial understanding. Explicit instruction and support may still be needed to help students use map scales and cardinal directions. Upper primary students should be provided with materials that include different projections and views and viewing angles, materials that use measured distances, cardinal directions, and abstract symbols with support, and materials that use multiple map formats and multiple scales. Teaching strategies and ways of working in mathematics I have modelled throughout the unit plan, lesson plan, and accompanying resources highlight explicit teaching and modelling the use of concrete activities using cardinal directions, location through grid referencing, using maps of familiar places to help orient and develop students' spatial reasoning, kinesthetic learning activities, instructional games for consolidating student knowledge, and encouraging students to produce their own maps, writing grid reference questions for points of interest. I have also used integration as a strategy. Integrating the mathematics concepts with curriculum subjects history and geography to develop student understandings and application of mathematical concepts in real life, solving real-world problems through inquiry-based learning. Follow-up activities would bridge students from understanding spatial concepts of figures in two-dimensional planes to three-dimensional objects in space, such as through exploring the world with digital technology. Geospatial data link physical and human attributes of points or places on Earth's surface, such as roads, other built features and rivers, and can be compiled, organised, stored, manipulated, and represented in many ways. Geospatial technologies such as geographic information systems, remote sensing, and global positioning systems, as well as internet-based mapping sites such as digital globes and geospatial visualizations, allow us to analyze and represent geospatial data in powerful ways. GIS, GPS, Google Earth, and other computer models, tools, and interfaces allow us to manipulate objects and ideas in ways beyond the two-dimensional plane. Interactive story mapping can be used to explore the features of maps and develop spatial thinking concepts such as bird's eye view, grids, directional language, location, place, direction, and distance by depicting various locations, landmarks, and features on the map and creating a story or using factual information to coincide. Terminology is an important teaching strategy, and educators need to incorporate additional spatial terms beyond relative terms, including geographic terms. Resources for primary students should continue with spatial language, but also begin to focus on helping students understand and practice spatial relationships. Students should collaboratively construct maps and use discussion to reason about their decision-making when choosing certain elements on the map, such as scale, grid systems, and symbols. Activities should use different types of maps of the same area so that students can discuss similarities and differences and their strengths and weaknesses. Students should observe their environment with unique physical characteristics of the environment identified. Students should begin to place themselves on the map and begin to make spatial connections. Because they are making the transition between realistic and abstract symbols, students may make mistakes when interpreting maps, so educators need to explicitly model how to read maps and show how symbols are developed and used. Specific spatial terminology that is important to use to support student understanding and achievement of learning intentions include words related to location, distance, orientation, and direction. For example, left, right, over, under, above, below, middle, parallel, tall, and short. I have also used cardinal directional language in all of my resources: north, east, south, and west. For older students, this language will involve geometric vocabulary of rotations, translations, and transformations. This is a slide that I used in my lesson. These are questions I asked during my lesson to check for student understanding and correct any misconceptions. Students were interpreting information contained in maps using a grid reference system to describe locations, so answered a lot of questions using grid references, such as B3. Questions also asked students to describe routes using landmarks and directional language. For example, the octopus is northeast of the ship, 1 square to 1 square. Examples of questioning that can be used to check for understanding include questions asking students to explain their spatial reasoning decisions, prompting their thinking about landmarks, distances, and directions. Specific questioning related to identity, location, distance, and direction should also be included. When bridging from concrete or pictorial representations of spatial concepts to abstract concepts, such as orienting cardinal directions in the student's physical world in relation to themselves, questioning should establish personal connections to concepts. For example, if I'm facing south, is east to my left or right? If I'm standing on the west coast facing the ocean, does the sun rise on my left or behind me? Spatial thinking skills in turn develop the proficiency standards of the Australian curriculum, including understanding, reasoning, and problem solving, and directly linked to the general capabilities, critical and creative thinking, literacy, numeracy, and information and communication technology. A focus on spatial thinking allows mathematics to become a more visual endeavour and connects with what real mathematicians do when they are exploring patterns in the world and making discoveries. By exploring the spatial aspects of mathematics, such as location and direction, we make it more accessible and engaging and more relevant. Thank you for listening to my presentation, and remember, stay spacey.